Good morning, honors chemistry students. I would like to begin our study of molecular geometry by examining the most basic of all molecules in the universe, which would be the molecule for hydrogen. To begin our study of molecular geometry, I want to review the bonding pattern that is established with hydrogen. So hydrogen is one of the Dr. Hofbrinkel gases, which has a chemical formula of H2. The next aspect, or the next diagram that I would like you to prepare for hydrogen, is the atomic energy level diagram, which you did for atomic structure and quantum mechanics, except today we're going to use it to examine the bond that's created between two hydrogen atoms. So in thinking about hydrogen, at least as far as protium, the isotope of hydrogen that we're going to use, has a nucleus which consists of 1 proton and 0 neutrons. And it has 1 electron in its highest occupied 1s sublevel. We're going to represent how that electron bonds with a valence electron from a neighboring hydrogen atom, which also has 1 proton and no neutrons and 1 electron. And in showing that shared electron pair is what we affectionately refer to as a covalent bond. And in essence, the octet rule states that when atoms gain, lose, or share electrons, they try to achieve the octet state to assume the pseudo-configuration of a noble gas. In this way, when two hydrogen atoms form 1 covalent bond, from the perspective of each hydrogen, they now have the full complement of electrons, which you would find in helium. Or full complement of electrons, correct, that's in helium. Helium is not in the octet state. However, it does have a completely filled energy level. So therefore, both of these hydrogen atoms have satisfied the octet rule. The next diagram that I would like you to prepare is to go back and prepare the orbital notation for hydrogen. And quite simply, we know that each hydrogen atom has 1 electron in a 1s sublevel. And it's those electrons in the 1s sublevel that form the basis of the shared electron pair, which is the hydrogen bond that the covalent bond that is being represented within this dashed box. The next diagram that I would like you to consider preparing for your molecular geometry lab is the electron-dot formula, or electron-dot representation. And in the electron-dot formula or representation, we represent this shared pair of electrons and that shared pair of electrons using symbols such as a dot or an X to represent that shared electron pair, which we affectionately refer to as a covalent bond. Another representation that I would like you to prepare is the structural formula. And my goal here is to get my students to examine several different ways of representing that shared electron pair that you will see in chemical literature. So this shared electron pair can also be represented with a line, and that line is what we affectionately refer to as a chemical bond. And chemists recognize that this line represents that shared electron pair, which is comprised of the 2 electrons in each of the 1s sublevels that come together to form a covalent bond. Next in our representations that I want you to prepare I want you to account for the number of electrons in this molecular system. So we'll say that's the electrons in the system. So in this case, each hydrogen has one valence electron. So we will say there's a total of 2 valence electrons in the system. However, we're going to compare that to the number of electrons needed for stability. And the number of electrons needed for stability includes the number of electrons each of these atoms would need to be stable. So each hydrogen actually needs 2 electrons each to be stable to look like helium. So 2 and 2 would be 4. So in other words, we know that there are 2 electrons in the system, but the electrons are arranged in such a way to reflect the fact that each hydrogen looks like helium to achieve stability. So in doing so, and in doing that, we do a simple calculation here of the number of bonds that would be predicted between each of the hydrogen atoms. This is an extension of what we would refer to as the Kelter strategy for determining the number of bonds in a molecule. So we examine the difference between the number of electrons needed for stability, the number of electrons in the system, and divide that by 2 electrons per bond. 4 minus 2 is 2, divided by 2 electrons per bond. The numerator 2 represents the number of electrons that must be involved in bonding, which in this case is 2. So since you have 2 electrons involved in bonding, and it takes 2 electrons to form a covalent bond, we predict that this molecular system would have 1 bond, which is reflected in each of those diagrams. Moving along, the next representation that I would like you to prepare is called the Lewis dot representation. The Lewis dot representation uses a line to represent a shared pair of electrons. You will see how this is similar to the structural formula, yet different as our molecules become more involved. But for now, the Lewis dot looks a lot like the structural formula. The next representation that we'd like you to prepare, or actually calculation, is to calculate the bond type that exists between the 2 atoms. In other words, what we want you to do is to compare the electronegativity difference between these 2 atoms. The electronegativity of hydrogen can be found on the periodic table, and the electronegativity of hydrogen is 2.20. And what we want to do is look at the electronegativity difference between the 2 atoms involved in the bond, which in this case, since both atoms have the same electronegativity, we can say that the difference between them is 0.00. We use this difference to classify the bond that exists between the 2 atoms. And in this case, an electronegativity difference of 0.00 represents a nonpolar covalent bond. Now, you may remember some time ago, I gave you a sliding scale which said that if the electronegativity difference is between 0 and 0.4, we say that a particular bond is nonpolar covalent. If it's between 0.5 and 1.7, we refer to a bond as being polar covalent, meaning that there's a separation of charge between the atoms that exist because the atoms do not share the electrons equally. In this case, the fact that the difference between the 2 atoms is 0.00, that means that these 2 electrons involved in the bonds are shared equally between the atoms. And last, 1.8 or greater, if the electron negativity difference is in that zone, we say that the bond is ionic. So once you've done that, the next calculation we'd like you to do is to look at the total pairs of electrons, excuse me, involved in, or the total pairs of electrons around a central atom. And so we do this calculation by saying the total pairs is equal to the bonded pairs plus the lone pairs of electrons. Now that may seem a mystery right now, but really we don't have a central atom. We have two atoms side by side. So we're going to run our calculation from the perspective of each individual atom. So for the atom on the left, we would say that the number of bonded pairs is equal to 1. And thus, there are no lone pairs because hydrogen only has one valence electron. So therefore, the total number of pairs of electrons in this molecular system is 1. Okay? And we go on to do the VSEPR structure. VSEPR stands for valence shell electron pair repulsion theory, which predicts the geometry of the arrangement of electrons around an individual atom. And so therefore, in this case, VSEPR theory does not make a prediction on one total pairs of electrons. But it does stand to reason that when you're looking at the geometry of the molecule, that the geometry of this molecule has to be linear, because since there's only two atoms involved in the bond, it only takes 2 points to make a straight line. So we would refer to this molecule as being linear, and we would say the bond angle between the two atoms is 180 degrees, which is the angle of a straight line. There is an accompanying theory called hybridization theory. But hybridization theory, there are no predictions for one total pair for hybridization theory either. So for now, we're going to not make a prediction for one total pairs with hydrogen, and we will just say that this is N/A or non-applicable. So the actual geometry of the hydrogen molecule, which is really what we're after, is the actual geometry, because that's what we're trying to predict, is the actual geometry of hydrogen is going to be linear. So we say that 2 points form a straight line. We say the bond angle is 180 degrees, and the hydrogen molecule has a linear arrangement of the bonded electrons. The last two columns you can look up. You can look up to tables. I'm interested in you looking up the bond energy. As well as the bond length. If you look this up for hydrogen, we say the bond energy is 435 kilojoules per mole. When bonds are formed, energy is released. And in order to break bonds, this is the amount of energy that has to be absorbed in order to break the covalent bond between those two hydrogens. The other aspect or quantity that I would like you to look up is bond length. Okay? And the length between those two atoms is 74 picometers. And lastly, two last columns here that I want you to consider. One is the AXE column, which you may not totally understand now, the AXE column. A stands for the central atom, X is for bonded pairs, and E is for lone pairs. Right now, we're not going to make any predictions of the AXE system per se, but essentially what you're going to have is a system where you have two atoms bonded together with no central atom, okay? And then last, we have the polarity. Some bonds are polar, some are not. Some molecules are polar, some are not. But since the electrons in each of these bonds that have been represented are shared equally, we say that the molecule itself is nonpolar. So that being said, that is the molecular geometry diagram out for the hydrogen molecule.